As we begin in Module 8 here, we're going to be discussing similarity, and we're going to start with dilations. And what we're doing here, dilations will be a non-rigid motion. We've talked about rigid transformations before now, your reflections, translations, rotations, but now we're talking about a non-rigid transformation, which is it changes the dimensions of a given figure. And a dilation enlarges or reduces a geometric figure. When the figure is enlarged or reduced, the sides of the image are proportional to the sides of the original figure. So everything will change by the same scale factor of dilation. So that is going to be the length, the ratio of the length on an image to the corresponding length of the pre-image. And it's going to be designated with the value of k. But the big thing here is, as we're calculating dilation, the scale factor, it's always going to be looking at the new divided by the old. Okay, so thinking about whatever my new image is divided by the old image, using that information will help us come up with that scale factor. So the value k, that scale factor determines if it's a dilation, enlargement or reduction. If the value is greater than 1, we would be enlarging. If it's a fraction, a portion of 1, somewhere between 0 and 1, it would be a reduction. Okay, so as we look at this example number 1, identify a dilation to find the scale factor. Determine whether the dilation from ABC to DEF is an enlargement or reduction. I would hope that when you look at that, you can see that DEF appears to be smaller. If it wasn't drawn to scale, maybe we were concerned about that. What we can do is take the corresponding side DE, right? That's that new item, over the corresponding side of the old item, which is AB, and that would be 2 divided by 6. Remember, the new divided by the old, which is equal to 1/3 or 0.3, okay, 0.33. So that's how we can determine. Now, since it is in between 0 and 1, it is going to be a reduction. So there you go, it was smaller. Looking here in this check, determine whether the dilation from WXYZ to JKLM is an enlargement or reduction. And again, if it's not drawn to scale, we simply take we have the new corresponding side over the old corresponding side, which would be 4/7, which is not greater than 1, so therefore it is a reduction, and we'll just say that the scale factor is 4/7. And that's how we can make these determinations. I did put over here, just remembering when we were talking about increasing or decreasing a percentage of something, how to calculate, understanding that the percentage, 57% would be the same thing as 0.57, and 500% would be the same thing as 5 times something. Okay, so as we look at this example, you need to make sure we're comfortable with percentages. Find and use a scale factor. Jalal is printing a banner for his school's wheelchair tennis team based on the design shown. By what % should Jalal enlarge his design so that the dimensions of the banner are 5 times that of the original design? What will be the dimensions of the new banner? Okay, so if this is my current banner, he wants to increase it by 5 times. So remember, everything is going to increase by that scale factor. So this side would be increased by 5, and this side would be increased by 5. You know, creating that enlarged banner using the commercial printer, the scale factor, enlargement by 5. So we're going to multiply everything by 500% or by 5. So there you go. 6 times 500% would be 30 inches. 14 by 500% or times 5 would be 70 inches. So my new dimension would be 30 times 70. And everything would have expanded by that same growth factor, scale factor. So in my portrait, Natalia wants to print and enlarge the family portrait to her mother, for her mother. By what percentage should Natalia enlarge the portrait so that the dimensions of the image are 2.5 times that of the original? What would be the dimensions of the enlarged portrait? So I'm going to multiply both dimensions by 2.5 and come up with my new dimensions. And it looks like we are dealing with centimeters. We have centimeters here, so and let's see, I have 24 times 2.5 should be 60, and then 18 times 2.5 0, 4, 9, 0, 6, 3, 0, 5, 4, so 45. So it looks like we multiplied 2.5 is the same thing as 250%. So it's one of these two, and then it turns out that yes, we enlarged, so it is going to be D. There you go. If you look, this one actually didn't multiply by 2.5%, so it only increased by a small portion of that. So there you go, being able to calculate that information based on the information they're giving us. Dimensions on the coordinate plane. To dilate a figure by a scale factor, okay, with respect to the center of dilation of 0, and that's where we're always really going to be working with, multiply the x and y coordinates of each vertex by k. Remember, everything in a dilation changes by that same scale factor. So the x coordinate would change by that value, the y coordinate would change by that value, so we are multiplying everything by that value. And if we look at this example, see they're showing us we just multiplied the old information by the growth. If I pick a point R, R is 0.21, and then as I grew, looking at if I multiplied R times 3, so the would be 3 times 2, because that's my scale factor, and then my x value would be 3 times 1. So my new R prime, should be 6, 3. And if I look here, that point is 6, 3. So that's how we can make that determination. How could I determine this scale factor given an image? Well, all I have to do is say, okay, pick a point here, or I will pick a point with P prime. That point is 3, 9, and the old P is 1, 3. And remember, I said it was the new over the old. Pick a coordinate here, and I'm just going to use the y value. The y value of P prime is 9. That's my new. The old value is 3, which is simply 3. So I can use that to determine that the scale factor actually was 3. So there's ways to use this information to benefit us and make things easier. Okay. So in this figure, it says dilating the figure. They've given us the vertices of a triangle, and it says find the coordinates of the vertices after the dilation by a scale factor of 1/2. That means we are going to take every bit of every one of the x and y values and multiply it times 0.5 or 1/2 to get my new values for the t. Okay, so that's what they did. The old value was -4 times 5. I'm going to multiply everything by the scale factor of 1/2. So -4 times 1/2 is -2. -5 times 1/2 is -2.5. So that is what we're doing with all of these to come up with our new locations. And if you look, that's half. Each one of these values over here should be half of what was over here. So that is a constant that we can understand. And now here in our check, they've given us, gosh, here we have x, which is, so as we do that, we multiply vertices x, y, and z find the coordinates of the vertices of the new image x prime, y prime, z prime after a dilation of a scale factor of 4. So I'm going to take each one of these and I'm going to multiply them by my scale factor to come up with my new image. So 3 times 4, negative 4 times 4, 5 times 4, 6 times 4, negative 2 times 4, 8 times 4, and I came up with my new image vertices, and that's how I'm able to come up with that information. So just knowing that everything changes by that scale factor, so we would multiply everything by that same scale factor. Looking here, it says find the scale factor of the dilation, and it tells me that a prime, b prime, c prime is the image of ABC after a dilation. Find the scale factor of the dilation. They've gone to a lot of work here to come up with a length of, they determine the scale factor between these 2 points. So we had the new, they said, hey, let's find the scale factor of the new value of a prime, b prime over ab. That's great, but that's a lot of work. Remember, if everything in a dilation changes by the same scale factor, I can pick any point on here and do it. So if I look at c prime, the x value is going to be 1, 2, 3, negative 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 3, 9. C is going to be negative 1, 3. I can take any one of those points, x or y, and I take the new y value. The new y value was 9, the old y value was 3, and I have just been able to determine that the scale factor is 3. I could do that with any one of the points and come up with that scale factor. So with that, they did the distance formula, not necessary at this point. I came up with the same scale factor that they did with a lot less work. So again, try to, using things and using the information they gave me to the maximum. So here, if we look at this, check the scale factor now. Again, I could do anything in here, but now I'm going to pick a side. I'm not going to pick one of these angles, because if I use the diagonals here, or the sides, they're not a straight line, so they're harder to count to find out how long they are. But I do know that this is my image, this is my pre-image, so I'm just going to count this flat one. Think about it. D prime, E prime is my new. What's the length of my new over the length of my old? And that would be 2 over 6, right? 1, 2, 3, 4, 5, 6, which is 1/3. So my scale factor is 1/3. That's just, I could have done anything to figure that one out, but I just decided to show you that it can be done with the length. Sometimes it's easy. So here, as we look on into, we'll continue on with similar polygons. Similar transformations is a transformation composed of a dilation, or a dilation and a rigid motion, but two figures are similar polygons if and only if they can be obtained from the other by a dilation or a dilation with one or more rigid transformations. When two polygons are similar, the angles and sides are related. So think about it, if it's similarity, it's going to be a dilation, so everything's going to grow or shrink by the same value. Okay. Looking at similarity statements are very similar, no pun intended, to congruency statements. Your similarity, this is my similarity symbol, says that ABCD is similar to PQRS. Okay, which means that in similarity, my angle measurements remain the same. So I know in this case that angle A should be the same as angle P. I know that angle B should be the same as angle Q because those are the corresponding values in the names. So I know which angles should match up, and then proportionally all my sides should match up proportionally. So the proportion of AB over PQ, right? AB over PQ is going to be the same as BC over QR, is going to be the same as SD over RS and is going to be the same as DA over SP. So those proportions will remain. All of those proportions should be constant. So here, looking at this, NP, we go this way. We go NP, QR, and then we go UVST. So I know then that angle U should be congruent to N. Angle P should be congruent to V. Q should be congruent to S. And then T should be congruent to R. And I can look at that. I was able to sort of figure out where it's at in my shape, but N, U, P, V, Q, S, R, T. Those are what corresponds. So again, angle U, angle V, angle S, angle T. I don't know where my angle measurement. There we go. For some reason it disappeared. So there you go. That's how we would look at that. Now write proportional statements. Now my proportions should be, so my proportions would be UV over NP should be equal to VS over PQ, which would be equal to ST over QR, which is equal to TU over RN. Okay, and that all corresponds to the naming conventions of it. So let's see, looking here, determine whether NPQ is similar to RST. If so, find the scale factor. Okay, what do I know here? NPQ, N should be the same as R, according to the names, right? Q should be the same as S, and then by default, P would be the same as T, because remember, if two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. So that is an accurate statement. So then correspondingly, looking at the values, NQ over RS is 5/4. QP over ST is 5/4. And then PN over TR is 5/4. So all three sides are proportional. They equal the same scale factor. So therefore, it is a similar polygon, and the scale factor is 5/4. Now, if for some reason you get to this point and you put it in the calculator, it's going to give you a decimal. It's going to give you a decimal. It's going to give you a decimal. It should give you 1.25. So it's the same thing. 1.25 would be your scale factor. Looking here, determining whether this quadrilateral ABCD is similar to the quadrilateral EFGH. If so, find the scale factor. Let's see. I could take it says, this is my pre-image, this is my image, pre-image. The new, I can see that FG corresponds to BC, so that would be 12 over 8. Which equals 3/2, or 1.5, and then I would have 14 over 10, which is going to be equal to 7 over 5, which is a different value. So therefore, if it's a different value, it doesn't have a constant scale factor, so therefore they are not similar. Okay. Looking here, using similar figures to find missing measurements. Love the cross product property. We're going to use this a lot. Some of you referred to it back in 8th grade. 7th grade was the butterfly method. So we can just write our ratios into proportions, and we're able to determine what we're missing. So knowing that in this example, WZ corresponds to PS. Okay? WZ to PS. YZ corresponds to RS. So now that they have that determination, they went ahead and filled in the information. Then now we have a proportion where we can cross multiply. And then 6 times 16 is equal to 12 times 5y minus 12, or minus 2. And then they used the distributive property, then simplified, then they added 24 to both sides to get our numbers on one side and variables on the other. Then they divided by 60 to get y by itself, and it turns out that y is going to be equal to 2. Okay, so we're doing a lot of cross-product property, and I will tell you, when it comes down to taking tests and word problems, this similarity and cross-product property will help you. There's probably 15 questions in the ACT math portion that you can solve very easily with the cross-product property and similarity. So looking at that, in this diagram, it says find the value of x and round. So I've actually set it up two different ways here. Let's see here. It looks like JM to JLM to QST. So I know that LM over ST. Right here, LM over ST, right? The new over the old over the new. Maybe I should change that, huh? Let's write it as ST over ML. And then that would be, ST over ML. And then we're looking at JM, so we would have QT over JM, because that's the value I have over here. So JM QT, that would be the new over the old ratios. Either way, we are going to get the same values, but I wanted to be more consistent. So with that, okay, so if we filled this out now, I will tell you that it didn't matter we're going to learn as long as we're consistent with our ratios, this over this, this over this, we would come up with the cross product property of 2 times 6x minus 3 equals 3 times 4. If we were consistent with the new over the old, we would have come up with our fractions, our ratios, our proportion, and when we cross multiplied, we would have had 3 times 4 equals 2 times 6x minus 3. You can see that these two statements are the same here at this point. So as we continued on and solved, this would be 12 is equal to 12x minus 6. Adding 6 to both sides, 18 is equal to 12x. Divide both sides by 12, and then x is going to be either equal to 3/2 or 1.5. And there you go. And as long as we're consistent as we set up the ratios, it's hard to make a mistake here. Okay. Let's see here. Similarity for perimeter. If two polygons are similar, then their perimeters are proportional also. So not only their side lengths, those values, but you can assume their perimeter is proportional because it's linear. We're just adding the lines up. And then here, he gave us a little word problem, a little example. Jeffrey plans on going to the state fair this summer. He has downloaded a map to the fairgrounds that shows all the attractions. Jeffrey plans to visit the concert hall, probably the concert hall, the Ferris wheel, and the sports center. On the map, the distance between the concert hall and Ferris wheel is 9. Let's see here, the concert hall and Ferris wheel is 9. The distance between the Ferris wheel and the sports center is 8. And the distance between the sports center and the concert hall is 4. Okay, great. Describe his path. Looks like a triangle, right? Let's see, find the total distance. Well, right now on the image, the total distance would be 9 plus 8 plus 4, which is equal to 21, and it's in centimeters. That's where we're on the map. Now, if the actual distance between the concert hall and the sports center is 20 meters, so the concert hall and the sports center actual is 20 meters, okay? How far will Jeffrey have to travel to visit all 3 attractions and then return to the starting point? Okay. In this case, it looks like I have 20 meters over 4 centimeters. So it looks like 5 meters equals 1 centimeter, or 1 centimeter equals 5 meters. Okay? If that's the case, then I could take 5 meters over a centimeter and multiply that by 21 centimeters, which would, centimeters would cancel out, and I would end up with 105 meters is the actual distance to travel the perimeter of that triangle to see all cases. Now, you can go through this and you can see that they've done a little bit different math here, talked about it. I would say that I tried to be a little bit more straightforward with the actions and just thinking through the processes of what we're doing. So that's that cross product property. And if I wanted to think cross product property, I have 4, I have the new is, I'm trying to figure out how far am I gonna walk around the new triangle over the old triangle. And then I would say that the old distance, right, or I'm sorry, the new distance over the old distance. If I were to cross product property that, let's see what would happen. I'd get 4x is equal to 420. If I divide both sides by 4, right, 4x, 420, then x is going to be equal to 105. So looks like there's a bunch of different ways. I just used the cross product property to come up with the answer. So similarity, similar polygons, dilations, we're going to use this cross product property a lot. The quicker you become comfortable with it, the easier it's going to be for you.